We'll just talk about how on the day of the event, it all continues. We've been talking about how you issue warnings starting 2 or 3 days out. It continues the day of the event. And sometimes it's hard, given the current operational environment in a forecast office, to do all the map analysis that you would really like to do. But I at least try to do what I've done here, and try to get a surface map, and then you can see I've drawn in smaller dark arrows here out of the panhandles up into southwest Kansas, southwest Kansas, then central Kansas up in Nebraska. Those are the 850 jets, the fastest flow at 850. And then the hatched arrow here represents a 700 millibar faster flow. And so at least if I can't do everything that I want to do, there's at least quick ways to put together as much information as you can on the same map. Still trying to validate all the stuff that you've talked about, because in the last 2 days you've considered all those photographs. You've thought in your mind, hey, I may need to draw this, with an exaggeration to one end or the other. But it all continues. And I think, while all the model stuff's great, and I'm going to show you some really cool local model stuff that we do that's actually helped with some warning forecasts, I think a lot of the forecasts can really be deciphered in the first 12 hours looking at the observed data. You guys already went through that. I don't know if you guys remember, I was sitting at the back row. I was late for your photography thing because I got hung up in a meeting. So I sat back and you guys went through all of that, how to anticipate where the upper lobe was going to go, where the elevated mixed layer was going to be. All of those things you can lay out in your mind and have that there as you continue to go through the model data and begin to assess, are the models helping me right now? Are they coming to the same conclusion that I am? And it's a good day when that's the case. You can continue on. But if you start seeing differences, that's when you have to dig a little bit harder, start thinking just a little bit more. And I always try to tell folks, for one, like the bottom 2 bullets, don't trust the weather. It will always do something you didn't expect. And work like you'll see your efforts in the coming years. And what that means is you never know when you're going to work a day that's going to require a service assessment, where the big tornado happened and 15 people died. And now it's your logs that are being scanned and put into the service assessment, where you can see there, talk to the neighboring office, we talked about tornado warning but didn't. Whatever that is, any maps that you had, try to work as if and look as much stuff and document as much stuff as you can, because you never know when you're going to work that historic day. And it doesn't have to be the day of days. It doesn't have to be a day like yesterday where we saw debris lofted to 25,000 feet in the air. It can be the unfortunate EF1 that goes into a mobile home park and 10 people die. And that might be the worst case that you ever work in an event. So all the days, any particular severe weather day, you kind of treat in the back of your mind that this could be one of those days that I will remember this case forever. I can see my documents in print forever. You need, as you get into the warning environment, as we get away from looking at what's going on, or what we think is going to go on, to what's actually happening now, is you need a strategy for the near storm environment. However, you can overlay some radar data some data onto the radar data that you're looking at. That's a great thing. But you really also need a meso analyst somewhere in the operation. So the radar operator just can't be expected to pull all of that information in through the whole zone that they're looking at. Now, sometimes radar operators will segregate stuff. They'll block off areas. In this case, we might say, okay, I'll take everything north of I-40. You got it all south of I-40, or you take the supercells, I'll take the squall line. So we can break up the warnings into sectors. But still, it's awfully hard to know everything that you could possibly know about the environment. So having a mesoscale analyst really close to the warning operators really is a must in an operation. This is the Tulsa Weather Forecast Office. Just looking at the warning operations, the River Forecast Center is in the background back in there. We're co-located with the RFC there in Tulsa. Main forecast operations are off to the right. But what I wanted to show you was the 2 warning workstations. That's the workstations that are here. The amateur radio station is over here. Communications, social media is here. And this desk in the foreground, that's the mesoscale forecaster in the Tulsa office. So it can talk to that person fairly easily, or both warning forecasters if they're up there. You can share information back and forth. And actually, we can get requests back from the warning team on how to do the near storm environment stuff. And that's what I wanted to show you, just to give you an idea on how some of that could work. We use our graphical forecast editor that forecast offices tend to use to create partly cloudy, a 60% chance of thunderstorms, high in the low 80s. We also create near storm environment grids from that, taking stuff from John Hart at the SPC, Israel Jurak helped, Ariel's helped with stuff, Patrick Marks has helped with different things, putting all that into there so that as the warning forecaster, you can give me requests on, if I'm the mesoscale person, and say, change the storm motion on that. I want to see what the helicity field looks like with a different storm motion now. Or recalculate something for me, and it'll pop up on my screen. So it's a nice way to do these calculations. It starts with just a local analysis and prediction system that every WFO runs, but then we can inject the actual observations into that objective analysis, and that's an example of the slider bars where we can QC the surface data that goes into it. We can fix obvious things that look bad to us, and in the end, we get to be able to do something like this. And this is from a few years ago now, but it's still really pretty cool. This, you see a warm front laid over eastern Oklahoma, dry line approaching from the west. The storm of interest is down in south central Oklahoma, and it's coming up fairly sharply to the north. And the warning forecaster's talking to me, they're like, hey Steve, rerun the storm motion on this stuff because the generic storm motion right now is not getting it, and I'm not sure what's going on here. Well, the first thing the warning forecasters are looking at is they're looking at the SPC page, which shows storm relative helicity to 150 meters squared per second squared to 1 kilometer. Not super high, but it's still at least positive. In actuality, though, by changing the storm motion, that storm is riding through negative storm relative helicity, because if you notice back on the SPC graphic, it's assuming a west-southwest storm motion. The storm was actually a left split from something out of Texas that was lifting up north into Oklahoma. So the storm relative calculations on the SPC page weren't going to be representative of that. And that's one thing I think as forecasters we make a huge mistake a lot of times, is accepting the storm relative helicity calculations that are presented to us. Most of them do take a right motion into it using a bunker's estimation of what's going on. And your first thought is like, well, you're already assuming a supercell if you're putting the right motion in, so why are you even looking at the helicity? Because you must think it's already going to be positive, or you wouldn't be picking the right motion. So it's kind of an inappropriate feedback on itself, where really we should really look at storm relative helicity as cell specific. So we put out this is before NWS chat was a big deal, we put out this little mesoscale discussion, talks about the supercell coming up, would support an anticyclonic circulation with the inflow side to the north, spotters ought to be adjusted accordingly. And sure enough, as the storm came up, look at the cell we got. We got a really pretty anticyclonic supercell passing over Lake Eufaula with an anticyclonic couplet, fairly strong. Not really sure why we didn't issue a tornado warning on it, except for the fact it's backwards, and that doesn't happen in Oklahoma. Otherwise, that was pretty strong. I kind of halfway expected that we might issue a tornado warning, but we didn't, and there was no tornado. But this really helped the forecaster in that regard, having the near storm environment person, the mesoscale forecaster there, able to recalculate a field for him and represent that back to him, saying, well, here's your answer. It also kind of prevented that thing that you hear about that causes airplanes to crash, when you got an indicator light that's flashing and they're all thumping the thing, like, I wonder what's wrong with that, as they fly the plane into the Everglades. I took away all the need to thump the indicator. They're like, this storm is looking funny, it's beginning to behave oddly. It doesn't make sense with 150 units of storm relative helicity. Once I showed them that, they were like, oh good, then this is an anticyclonic cell. They were perfectly tuned in on it, kind of lost before, then now focused in on it. So having that near storm environment person there to answer those questions is huge, and it can really augment how the warning forecaster makes decisions. Show you a couple other examples too, just so you can get an idea of how you can you can really get into the weeds with it. And we have some case examples that we shouldn't have done as well with storms as we did, but the near storm environment played into it, and having that mesoscale person sitting right there really helped. We had a kind of a raggedy little supercell coming into the area south of Tulsa. Here's Tulsa County up here. Here's the supercell coming into Okmulgee County. It has tornado warning on it, and there's other really sloppy convection going on coming into Tulsa, some of it with wind, but not too exciting. As the situation goes on, the messy convection is approaching the supercell. We've dropped the tornado warning as the supercell continues to degenerate. But we notice in the near storm environment grids, and I put this in NWS chat, that there's a zone of weaker cap and higher instability ahead of that cell that's roughly running from downtown Tulsa to Coweta, that if that cell can live to that line, it can take advantage of that environment that's set in there. So I've told that to the warning forecaster. I'm like, I don't know, but if that thing gets intact to near that line, the cell could begin to evolve again, look more organized. Something bad could basically happen if that cell can get to that line. So a few minutes later, the cell, and what you're looking at here on the left is the 0.5. And on the right looks like 8 degrees, so you're up higher, closer to 10,000 feet. This was the NWS chat stuff. TWR showing a good bow with increasing velocities northwest Okmulgee County. This will interact with the South Tulsa County cell soon. One of the TV stations says, hey, we got good mid-level structure over South Tulsa County. He's referring to the almost bounded weak echo region there. The cell is showing some signs of life as it approaches that zone. And then after it crossed the line, it actually produced a tornado scarily very close to the white line. And this is a picture later on that shows a little couplet after it's left Broken Arrow heading northeast toward the radar. What was interesting about this was the warning forecaster who did this let a few months pass, thought about writing a case study of it, and he went back and he looked at the radar data and he said, I have no clue why I issued that warning. He said, I look at this now and I have no clue what radar data prompted that. And he goes, it was all the near storm environment discussion. Because it met no criteria that I have whatsoever for a tornado warning. Pretty sure and I think we ended up high-end F1, maybe even F2 in Broken Arrow. It wasn't the super headline of that year, but we probably saved missing a tornado in the metropolitan area because we aggressively attacked the near storm environment with that stuff. We also use some local models in our warning environment, and it's something that's not officially sanctioned. It's not anything that's supported, but we try it. We typically can run 3 models, sometimes 4, and it's not important to go through. In fact, this might not be the current true configuration of these 3 models, but what I try to explain to my non-meteorological friends is it's kind of like that. You start these models from totally different backgrounds, totally different perceptions, totally different whatevers. And if they can converge on something, you kind of have something important. Same thing with the political parties. If for one day, if all 3 folks there actually said the same thing, it would probably be a day to mark down on your calendar. So it's how we use that to try to get consensus a little bit on some of this. But this was another example from last year using these local models where, again, using near storm environment stuff with these local models helped save us, I think, a tornado warning that we might not have performed as well on otherwise in Tulsa. This are output from 2 of them. These are updraft helicity tracks. And it shows a couple of the models streaking out rotating cells across the north part of the Tulsa metro area and on northeast. Of course, we all know that these mean absolutely nothing if the meteorologist can't assess that the environment supports this. And so the models by themselves are nothing if the meteorologist hasn't assessed the real environment. But we saw the environment rapidly changing. In this case, it's at 6:30 in the evening. Thunderstorms are starting to form west of Tulsa. Tulsa had not been in a severe thunderstorm watch, but we got a local extension of it. It was one of those days where it had rained and no one was sure if we were really going to redevelop the instability. Now all of a sudden, we're using our analysis things like, hey, we got 2,000 CAPE where we only had 200 CAPE an hour ago. And we're also now starting to get just enough storm relative helicity in our grids to make us think we have a tornado threat developing. At the same time, the local models are kind of catching on to that. So we're going rapidly from this is kind of a quiet, dead evening to maybe something's going on. This is kind of where 1979 met 2016. This is where basically the warning forecaster using the lemon technique is looking at an appendage sticking out south of a strong bounded weak echo region, which is what the Weather Service really relied on before it had Doppler velocities. And it was meeting up with those local storm models, those local models and the near storm environment grids. And I'm sitting there, I'm at the Mesoscale desk, and I hear click, 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 and I look up and I'm like, hey, what are you doing? He goes, I listened to that stuff you're saying behind me. I can delete the word since it's being taped. I shouldn't say whatever it was. But the point was, he's like, everything you said, helicity coming up, CAPE just all of a sudden went through the roof, and this cell is suddenly exploding like a supercell that means it. It's going through all the physical structures are changing. I'm issuing a tornado warning for Tulsa. It's like, well, we don't have a lot of velocity yet. He goes, I've got everything. I got environment. I got the evolution. I'm good. Here comes the tornado warning. I'm like, okay. So this is when the 70s kind of met now, where we had the old-fashioned lemon technique mating up with everything else that we're doing. So here's the NWS chat, tornado warning coming for parts of the metro. There's the warning. And the emergency management folks say we're activating the sirens on the north side of Tulsa. Eventually the storm still looking a little raggedy, 10 minutes after the warning. But one of the convection allowing model finally came in, and on chat I just said the most sophisticated model we have, shows this going on, shows the rotation values really becoming high on the north side of Tulsa. We've had enough good luck with the use of these models over the last 3 or 4 years that the Channel 6 station, the CBS station in Tulsa, actually went on the air and said, hey, the Weather Service in Tulsa is running experimental techniques. They're really confident that a tornado is going to form on the north side of Tulsa here in the next few minutes, folks. We got to be ready for that. That's when the cell is still looking like that. It's still It's still kind of ragged. I got a text on my phone that said, hey, Travis Meyer just talked about you guys, and he's talking about your models. And then eventually we had an EF2 tornado. It ran from 713 to 755, 20 miles on the ground, 4 injuries. It threaded its way through Tulsa. It didn't get some of the highest population areas. But still, it was an event that we went from at 6 o'clock in the evening, not being in a watch, to a rained out environment, to by 6:30 we're like, hey, the environment is rapidly changing. We got to be on guard here, to like 6:45 we're issuing a tornado warning, and by 7:13 there's a tornado in Tulsa. You got to stay up with the near storm environment because it's changing fast, and it can really impact how you make your warning decisions. Here's another case. This goes in the example, and Ariel knows Mike Teague. He's our data acquisition program manager. Those are basically dinosaurs, and you can leave that in the tape if you want. That I call him a dinosaur on tape. But it's one of those, back 20, 30 years ago, you didn't always have degreed meteorologists at the office. You had folks with military background, all the training, all the smarts, just didn't always have the school. Mike fits in that category of being very smart about severe weather, and he always would tell you that if a storm has made a tornado once, it's likely going to do it again until it's dead. Don't let your guard down on it. And sometimes it's hard to know when to invoke that, but we call that the Dapham's Law, because it almost just needs to be dead. And I don't know, we can leave the cameras going, but just a quick discussion. What goes on there when a storm has made a tornado one time and it looks like it's about dead, and now it's trending, and you think it's gone, all of a sudden there's a rapid rejuvenation. What's going on with that? Yeah, it's cycling. It can cycle pretty easily, though. It seems like sometimes the next time. What process is going on in there? And if anybody knows the complete process, it's probably wrong. But what kind of guesses do you think? And I get another question too. Is like, how fast can it cycle? Sometimes, like we talked about, it may take some time to finally get to that tornadic phase. If it's going to recycle, is it generally faster or slower than when it tries to recycle? From let's say it took an hour and a half to get the first tornado. Is it going to be an hour and a half to the next tornado? You guys are shaking your head no. It's going to go faster if it's going to do it. So I don't know. Background vorticity. You've already accumulated enough vorticity in the vicinity of the cell that it doesn't have to reorganize everything. At the beginning, it had from scratch. It had to pull everything in around its near storm environment to make all that work, and the environment had to set up right. The second time it goes to make the tornado, the environment has kind of already been established. And so this happened to me a few weeks ago, and it was really funny. This is a little cross section. This storm, this is in northwest Arkansas. And they were low top supercells, capable of making a couple tornadoes. This was about the time of the tornado, the next attempt of the tornado. And then you can see it immediately comes down, and it doesn't really go back up. And that's about the time the warning is going to expire. So the velocities have cratered, the core has come down, the structure is really starting to get ragged, and just naturally it's within 30 seconds of when the new warning has to go out. So the room said, Steve, you've lost the core, you've lost it, that, and the other. And I said, yeah, but I don't trust it. That was like one of the bullets from the first slide, don't trust the weather. So eventually it comes back, and right then, that's when it was really looking some of its worst. And it comes back, it actually produces a little tornado in there, and then it even intensifies further to make a longer track EF2 tornado in northwest Arkansas. So I just wanted to make the point that even though that's not the best case or example of it, but just the idea that once it's tornadoed once, you really got to make sure you want to let loose of the tornado warning. You've got to make sure that, and again, that goes back to the near storm environment grids. Has it left the environment? My assessment was the environment was no different ahead of the storm than it was behind the storm. I could see no reason for that storm to decay. Now, if it was crossing a warm front and it's about to be in 45-degree dew point air, you might be a little safer on that, although I came close to canceling a tornado warning once when the storm was like a county and a half north of the warm front, and I felt stupid for continuing. And right when I was going to the cancellation thing, we got the report of the tornado. I was like, man, that was quick. I mean, it was the last tornado it did, but it took partially off a roof off a high school in Okima, Oklahoma, and it was way north of the warm front. So you never really know how deep the cold air is to know enough when the threat's really done or not. Issuing warnings is hard. It's a tough thing. talk a little bit about radar data too. What do you think you got there in this display? You've got Paducah radar data, you've got 0.5 degree elevation, so you got the lowest storm relative velocity and reflectivity information on there. What do you have on the, what do you have going on there?
Looks like you have two couplets, but there may be a possible tail core which you're getting ground reflectivity, correct? Like
You're getting a new Mesoscale from?
or that.
Yeah, that's could be all of the above when you start working through all that stuff. Any other possibilities? Especially when you sit on the warning desk and things are happening so fast, and you've got people like Ben that are calling in reports and they're seeing stuff, and you're trying to simulate so much stuff, and the mesoscale forecasters behind you chattering away about stuff. You're processing a lot of stuff. Actually, what you have there is the mesocyclone in the hook where it ought to be actually a tornado, and the forward thing is all bad data. And you can start looking at it, it's like if it were a newly developing mesocyclone, at some point in its evolution, it would try to start making a hook, because if the air was really starting to spin, the reflectivity would start to respond to that. And that's been there, and you guys didn't have the benefit of knowing that. But looking at that over the couple minutes before that and a couple minutes afterward, the reflectivity stayed just a nice straight line there. That's an indication, or this is a case where the radar lied. The radar is actually composed of a main beam that we collect most of our data from. But just like any radio engineer, electrical engineer would tell you that any kind of transmitted wave comes in lobes and comes. It's not just a clean thing that goes out there. So that's what the 88D in a cartoon-like version would look like, with the main beam in red. Then you've got side lobes coming off on the yellow and on the blue. If you looked at it on end, it would look something like that bullseye-looking configuration there in the little box inset. The radar was designed to ignore everything in the side lobes, but it doesn't always do that. It can't always reject everything. There's a couple of special cases when that happens. This is an actual measurement of the KOUN radar back in '96. We don't have very many measurements of the actual radar radiation patterns, which we really should, so we really understood our data better, but we don't. But the design specifications say that any of the outlying lobes have to be suppressed down to 27 dB. So, and that's kind of, you see the 27 dB line marked there at the first lobe, and then it should be suppressed even more as you go further out. So if you take the two-way path, it was suppressed 27 dB on the way out, it's suppressed 27 dB on the way in. You're at about a 54 dB difference. And what happens with the radar is that if what's in the main beam is 54 dB, roughly 54 dB higher than what's in the main beam is 54 dB lower than what's on the side, the power can sneak in. And so you start getting return from the side lobe while the main beam is pointed into the low reflectivity area. Now, where does the radar know to plot that? All it knows is to plot it to where the antenna is pointed. It doesn't know that signal came from over here. It's pointed right here, so it's going to take whatever it gets from over here and map it there. And so you begin to mismap data. Now that's been known for a long time. We always thought about it in the horizontal, and that's where you see here the storm in Muskogee County. This comes right out of the National Weather Service training on side lobe contamination, where the side lobe is what extends out horizontally as you imagine the radar sweeping around and the sweep coming around clockwise. And then you've got a triple body scatter spike there that also is kind of cool in that picture. But what you have going on is that the main radar beam is pointed right here at this point, but the side lobe is in that core. There's more than a 54 dBz difference between what's in the low reflectivity and what's in the core. You begin to get some side lobe contamination. But it's pretty rare. You don't see that a whole lot on the radars. But where you do see it all the time, and we're just now getting smart enough to know that that's what it is you see it right where you don't need to see it. And that's in the vertical, from the overhang in a supercell. That's where you've got high reflectivity aloft that's on top of the low reflectivity that's in the inflow by the hook. So you set up an environment that's really conducive for side lobe contamination in the inflow part of a supercell, exactly where you really don't need that to happen. If you look at this example, we go back to our twin circulations there, our twin couplets that we have. And this kind of gets messy. I have a reflectivity cross section in the top and a base velocity cross section down below. Down here, the beam is pointing at a zone where I've got it filtered, so there's really no echo there. It's really about -1 dBz there. You contrast that to what's above it, that's more on the order of 55 dBz. So it's that difference, that's that side lobe that's up in the higher altitude in the overhang of the supercell that is letting some data leak into the main beam. Well, the power is not particularly high. I mean, it's being suppressed 54 dB in and out. But the power, even though the power is really limited, the velocity data that are attributed to the power come on through. And so the velocity actually ends up having more weight in the whole scheme of things. So you can mess up the velocities easier than you can the reflectivity. So in this case, these reds that you see here next to the green are actually these reds up here at higher altitude that came in, that leaked in through the side lobe and now get plotted down here and look like two couplets. Which is really, it's a huge stress on the warning forecaster. First couple times that happened in our office, we had something like this where you just had the forward side lobe looking couplet with nothing corresponding in the hook. But you start going, well, you know, there's time lag between the reflectivity and the velocity, and it could be a forward flank meso thing. All this stuff's going on. I said, I don't think it is. And the guy just looked at him like, you swear it's not. It's like, well, no, I can't swear it's not. I said, you issue what warning you need to issue on. But I really don't think so. And over time, we've gotten more confident in our office, and I think other offices too. I co-authored a small extended abstract with Don Burgess, and we took this to the AMS Radar Conference, that's kind of what we're looking at. So I get really hesitant anymore when just even you're looking on your phone and you see people tweet, oh, giant tornado headed towards this town. If I can't look at it in 3 dimensions and try to understand, am I getting side lobe contamination or whatever, I refrain to make a whole lot of comments about it because the data are more complex than you think. One thing you can look at is the spectrum width. The spectrum width will always be a mess in that example. So the upper left here is the spectrum width. You can see maxed out here in the white. That's right here in the couplet. And I've taken the highest spectrum width and remapped it on top of the reflectivity there. And you can see that the higher spectrum width immediately stops once you get inside the cell. It helps you identify that those are bad data. So our key points from the extended abstract that we did is that basically be careful of any velocity data where you've got 25 dBz or less of echo, because 25 dBz with the 50-55, you're getting toward the theoretic high end of the reflectivity that you might see. So we get more nervous about that. We would say really inspect those data. Don't automatically accept the velocity data that you see with the 25 dBz or less returns in the inflow area.